All right, let's start. Good morning. This week we're going to transition to this very nice application of the spectral theorem, which is singular value decomposition. But before that, I want to finish our discussion of the different items in a spectral theorem, some heuristics. I'm still debating as to whether or not we should discuss quadratic forms, which is somewhat related to the spectral theorem. But even before that, I think for sure we should discuss this spectral decomposition. Okay, there are 6 items in the spectral theorem that I wrote last time. Typically, if you can remember 1 or 2 of them, the rest you can sort of deduce. But maybe we should do some sort of a review, because spectral theorem, it is so mysterious in a sense that I feel like it ends up being rather useful to be able to memorize it and sort of say it out loud. And I hope you appreciate the power of this as well. So say for whatever reason, you're required to, you need to compute the angle between 2 eigenvectors of some matrix. Okay, in general, this is a rather arduous matter, right? But in the case of spectral theorem, so in the case of a symmetric, A transpose equals A, you have automatically that any 2 eigenvectors, insofar as they are associated to this distinct eigenvalues, are orthogonal. They are perpendicular automatically. So this allows you to sort of fast forward a lot of calculations. And I think part of why it is rather hard to digest the spectral theorem is that to verify it numerically, you need to do a lot of calculations in general. So this is not like row reduction, whatever. It's like row reduction is like 10% of verifying the spectral theorem for a given specific matrix. So that makes it, I think, hard to sort of digest what is being said. With all this said, I want you to perhaps remind me some of these items. What can I say? If I have an n by n symmetric matrix.
Eigenvalues need to be real.
Okay, eigenvalues are real immediately, okay? No shenanigans with these imaginary numbers, complexes, all these things. All eigenvalues are automatically real. Okay? So the moment you see sort of like a symmetric matrix, you should have this, warm, fuzzy feeling inside you. It's like, oh, things are nice. I'm not going to need to compute everything. I can still say things, okay? What else? Someone else who haven't spoken yet. I have a symmetric matrix. What can I say?
The geometric and algebraic multiplicity are the same.
Very good. So GM equals AM, okay? In general, GM could be less than AM. That's a worst case. But for any eigenvalue, if you have a symmetric matrix, GM is going to be automatically the maximum possible, which is AM of the eigenvalue, okay? Any other things I can say? I have a symmetric matrix. Someone who hasn't spoken yet.
For any 2 distinct eigenvalue, their eigenspace is perfect.
Very good. Okay. So let's write it like this. If I have 2 distinct eigenvalues, one of them could be 0, okay? That's not a problem. But I know that the associated eigenspaces are going to be perpendicular automatically. Very good. We had some more sort of dubious items on the right board. We need 3 more things that are somewhat related. Someone else.
There is a orthogonal or an orthonormal eigenbasis in it.
Okay. Item 5 is sort of like a simpler version of it. there's an eigenbasis of Rn, or of A, you can say as well. What does eigenbasis means? What does it mean? Well, it means I have sufficiently many independent eigenvectors of A. Okay? That is to say, I have n linearly independent eigenvectors of A, and maybe some of them are associated to this eigenvalue, some of them are associated to that other eigenvalue, whatever. That doesn't matter. What does matter is that they all solve the eigenequation and they are linearly independent. But in a sense, just let's review this very fast. If you have 5 and if you have 3, that gives you 6 basically. So here's the idea. 5 plus 3 gives you 6. Here's why. Well, in fact, I don't even need to assume 5 yet. Let's put it like this. In fact, okay, let's do it like this. As a consequence of 2, what I can say is this. I can take one eigenvalue, say lambda 0. It's a fixed eigenvalue. Well, I can look at the eigenspace associated to lambda 0, right? So this is the eigenspace associated to lambda 0, which literally is defined as the null space of lambda 0 identity, or lambda 0 I minus A. Okay? And I know that its geometric multiplicity is the same thing as the algebraic multiplicity, which means the dimension of the eigenspace associated to lambda 0 is the same thing as gm of lambda 0. That's the definition. But it's also am, the maximum possible. Am of lambda 0. Now, this eigenspace, okay, is some subspace, ultimately, of Rn. And we know by now that any subspace has an orthonormal basis for itself. Right? You can just look at this matrix, solve. It's going to give you a bunch of free variables. Based on that, we can come up with a basis, okay, for the eigenspace. But then we can apply Gram-Schmidt to it, which ultimately is going to give you an ONEB for the eigenspace. Okay, let me write it. Row reduce, etc. To find a basis. How should we write this? Let's write it like this, beta. In fact, let me write it like this, in fact. Beta sub lambda 0. Just be clear about the dependency. This is going to have exactly this many eigenvectors. So 1, beta sub lambda 0, 2, dot, 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 beta sub lambda 0, comma, am of lambda 0. Okay, that's a basis for the eigenspace of lambda 0. In particular, what does this mean? Each of these vectors in my basis for this subspace is an eigenvector, and they're linearly independent. That you get by row reducing this guy. On top of that, we can apply Gram-Schmidt to it. To this basis gives you some ONB for the eigenspace. ONB, let's write it U sub lambda 0. U sub lambda 0, 1, U sub lambda 0, 2, dot dot, U sub lambda 0, and then AM of lambda 0 of this eigenspace. Okay. But then that's where we're going to use, I think, at this point, 3. And 3, let's say. Well, for each distinct lambda 0, for each distinct eigenvalue, I have one ONB for the associated eigenspace. I know at this point that this, for instance, is perpendicular to this is perpendicular to this, whatever. But then for each distinct eigenvalue, I have one basis like this, that is ONB. And if I were to compare one vector from one eigenbasis associated to this to some other one, that's going to be perpendicular also by item 3. And so putting all of these bases for subspaces together, I'll have one large basis that's going to be a basis for everything. Okay? I'll write it like this. I'll write it explicitly for once, because sometimes these indices, I think, make things confusing. This is what I mean. Say these are my distinct eigenvalues. Okay, these are distinct. Just because you have symmetric doesn't mean that your eigenvalues are going to be of multiplicity 1 all the time. Some of them might have AM 2, 3, whatever. So I have U sub lambda 1, okay, and ONB for the eigenspace associated to lambda 1. Then I look at the eigenspace associated to lambda 2, do all this stuff again, get another ONB for the eigenspace associated to lambda 2. ONB for the second eigenvector, eigenspace. Okay, you keep going like this, and finally I have U sub lambda p. Lambda p, comma 1, U sub lambda p, comma 2, dot, 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 U sub lambda p, comma algebraic multiplicity of lambda p. Again, it's an ONB for E of lambda p. So for each eigenvalue, I look at the corresponding matrix I should be looking at for the eigenspace, do the row reduction, get some basis for the eigenspace. To that basis, I apply Gram-Schmidt to get an ONB for the eigenspace. I do this for each eigenvalue. So I have a bunch of vectors like this. Then I put all of these together, and that gives me the ONEB for Rn. Okay? So start with this, these, you concatenate all of them. And then finally, you're going to be left with this one. Okay. What does this mean in this notation? So I'm using two subscripts here. The first subscript tells me the eigenvalue that this vector is supposed to be an eigenvector for. The second subscript is giving me the which basis vector I'm looking at for that specific eigenvalue. And so here, applying A to lambda I, comma j, is going to give me lambda I times this vector. Okay? They are normalized because I'm looking at orthonormal. And then if I were to take two distinct indices here, or two distinct eigenvalues, they're going to be orthogonal. And then P, Q. Okay, that's what ONEB is. How to visualize this? Well, each of these eigenspaces, okay, are subspaces of Rn. They don't need to be one-dimensional, but here's one way to think about it. So here's the origin. Maybe here's a two-dimensional space that is the eigenspace associated to lambda 1. Then I have perpendicular to it. It's harder to visualize, but I'm going to try to draw some sort of a picture here. Like this, I guess. Okay. Okay. This is harder to sort of visualize, but imagine that this three-dimensional space is perpendicular to this plane. Okay. Then I have some other eigenspace. Maybe it's one-dimensional, somewhere like this. I'll do one more. Let's add one more plane somewhere here. The point of item 3 is this, okay? If I were to look at the angle between this and any vector in the blue, that's going to give me 90 degrees. And likewise, this is going to give me 90 degrees. And the angle between this plane and this plane is going to be 90 degrees. And likewise, this is going to be 90 degrees to everything also. This is like a higher dimensional picture if you want. I'm just compressing everything to 2 dimensions. That's what item 3 tells me, okay? All I said over here was this. Okay, I have finitely many subspaces of Rn, I'll write that here too, that I know are pairwise perpendicular to each other. So in this case, okay, Rn seems like this is 1, 2, 3, 4, 5, 8. Seems this is like an 8-dimensional picture. I have finitely many subspaces, in this case 4. Okay, I know that any two of them are perpendicular to each other. And at this point, I also know by Gram-Schmidt and all that stuff, I can always come up with an ONB for each of these separate subspaces. All I did here was I applied Gram-Schmidt this, to get an ONB for this, ONB for this, ONB for this, and ONB for this, and I put them together. That is my ONEB. Okay? So maybe I can try to draw. That's your ONB for E lambda 1. Then you took a vector in this eigenspace, normalized it. Okay. Then you take two vectors like this, normalize it, and so on. And then you take three of these. That's again an ONB. You put all these vectors, and that's my ONEB. Make sense? And also, just to do some sort of a sanity check, algebraic multiplicities of all eigenvalues in any case are going to add up to n, right? Because ultimately, these algebraic multiplicities are exponents of linear factors in the char poly of the matrix. Char poly of an n by n is always an n degree polynomial, which means am, so the sum of ams is going to be n. And so here I have am of lambda 1 many vectors. Then I add to it am of lambda 2 many eigenvectors, and so on. So if I add all of these together, that's going to give me n in total. Okay, that's sort of like a sanity check. Any comments or questions about this?
So if that gives you n, then why not just skip to that part? Because if you had, because you could easily find an orthonormal basis for r to the n if you just used, 0, 0, 0, 1, 0, 0, 1, 0.
Yes, but they need not be eigenvectors. Not only am I looking for an ONB, like you said, it's like if I was just looking for an ONB of Rn, I could just take the standard basis vectors. That's fine. I also want them to be eigenvectors of A. Because if I start with an arbitrary n by n that is symmetric, it is not necessarily true that it's going to fix the standard basis vectors. I want directions that are fixed under A. The reason why I'm doing this splitting is because, for instance, A preserves this eigenspace. So what I can do is, instead of looking at my whole system, I can look at the decomposition into eigenspaces, and each of these are their own sort of subsystem that is self-sufficient in a sense. So if I'm trying to understand, for instance, the dynamics of A acting on Rn, well, it has a bunch of different components that are kind of independent from each other under the action of A. So just to remind you this example, I think I'll erase this. Okay, 2, 1, 1, 1. It's a symmetric matrix. Right, so we just computed it has two distinct eigenvalues. So like this, okay? Since in this case both of these are eigenvalues, the algebraic multiplicities have to add up to 2. That's the total dimension, which means both am and gm for lambda I is going to be 1. So it's going to look something like this. Okay. Remember, I told you that because this lambda 1 is larger than 1, under A, this line is going to be preserved, and it's going to be expanded. And here, the second eigenspace is going to be contracted. Okay. So this is essentially the same idea, except in higher dimensions. In higher dimensions, what could happen is that you could have some expanding directions, some contracting directions, and some sort of directions with eigenvalue 1. In fact, it turns out that the directions where the eigenvalue is 1 is the hardest. These are sort of what are called center directions in differential equations, for instance. So even though A acts on this whole space that is two-dimensional, instead of looking at the horizontal or vertical, because you see, 2, 1 is where A takes 1, 0, 2, right? It's the first column. You see, it's not preserving the horizontal, or it's not preserving the vertical. It is preserving this direction and this direction for whatever reason. So you're sort of reconditioning your vision in such a way that the basis directions are preserved under A. Okay? Does this make sense? This is like the main export of this course, okay? Spectral theorem and why it works or why it's important. Comments, questions? In week 15, we're going to see some examples of, or maybe in week 14 actually, in 2 weeks, we're going to transition to linear dynamics, and we're going to look at some models where we sort of use these ideas. Okay. Now, there is a final item that I wanted to discuss, and then based on that, I want to discuss the spectral decomposition. So what is this fourth item? Can someone remind me? Someone who hasn't spoken yet. Yeah.
There's an orthogonal matrix Q and a diagonal matrix D such that A equals QDQ transpose.
Okay. Now, just like with any other procedure, algorithm, whatever, in this case too, whatever you do linear algebraically can be represented as a matrix factorization. Okay? That's all there is to it. And in fact, this 4, 5, and 6, they're pretty much equivalent, actually. So orthogonal Q, diagonal D, such that A equals Q, D, Q transpose. Okay. Now let's try to make sense of this. By the way, before the midterm on Friday, I'm going to do some sort of a review about these different sort of adjectives, orthogonal, symmetric, orthogonal projection, oblique projection, and so on. We're going to look at which one implies which as well. It's kind of confusing. So I want to spend more time on these different adjectives also. But for now, let's try to sort of make sense of this equation. I'll just say this, okay? In fact, this fact that you have an orthonormal eigenbasis is pretty much the same thing as 4. What you do is, you're just going to take this ONEB, I erased the B, you take this ONEB, put that in a matrix, and that's going to be your Q. Okay? So 6 implies 4. But just to be reasonable, let's suppress these two indices in our ONEB that we obtained using this idea. So row reduction on each eigenspace, and then Gram-Schmidt on each eigenspace, and then concatenate. Let's just re-index everything such that I'm just using one index. Okay? So now it's much more pleasant to look at. Okay? It's the same thing that I wrote before. I'm just using one index instead of two. But then the other thing, so the eigenvalue sort of gets messed up, you see. In any event, I'm not going to do this because otherwise eigenvalues get messed up. Let's do it like this. I'm going to keep this notation that I used before. 1. These are my eigenvector basis vectors that are also eigenvectors associated to the first eigenvalue. Then I have the rest, okay? And then I'm going to be left with, finally, u sub lambda p am of lambda p. That's my ONEB. And like I said before, I can sort of suppress all these indices and write it like this as well, if I want to be fast. Though the one reason why I'm preferring this notation over this notation right now is because I want to plug in, I want to apply A to one of these vectors, and ultimately I want to end up with which eigenvalue is the related one. And so if I were to apply A to the first basis vector in my orthonormal eigenbasis, well, this is going to be lambda 1 times the same vector. Okay, I'll do a couple more. If I were to apply A to the second vector here, again, the multiplier is going to be lambda 1. And if I were to apply A to the last vector, I get lambda p times the vector that I plugged in. Lambda p, am of lambda p. Now consider Q to be the n by n matrix whose columns are these. N by n matrix. Whose columns are the ONEB vectors in the given order. Okay, the order matters here. By the way, I should mention, as I was editing the video where we, the video for the lecture where we did this explicitly, I realized where the mistake was. It was just that when I was writing that V matrix, I switched the places of the eigenvectors, and that's why the calculations messed up. Never mind. So we have this. Okay? This you need to remember. Whenever you have an n by n matrix whose columns are orthonormal, okay, such as in this case, that matrix is going to be orthogonal immediately. Okay? Remember this. Q, therefore, is an orthogonal matrix. And what is the definition of that? It means Q transpose is identity, and Q transpose Q is also identity. Another way to say this is to say that the inverse of Q is the transpose of Q. Okay? This is really nice. Orthogonal matrices are really nice because of this. Because why? Just to reiterate, in general, computing the inverse of a matrix is a pain, right? It's like you need to sort of do this augmented matrix, you need to do the row reduction, whatever. It's a complicated procedure. On the other hand, taking the transpose of a matrix is rather nice. You can just do it in one step. Okay? And so orthogonal matrices are special in that their inverses are very easy to compute. This is, for instance, the case for permutation matrices. The inverse of a permutation matrix equals its transpose, and permutation matrices are orthogonal matrices. Okay? So that's my Q. That's going to be my Q in the item 4. And why do I have here Q transpose? You can think of it as Q inverse as well. Since Q is orthogonal, I could have written QDQ inverse or QDQ transpose. They are the same thing. But since transpose is a much simpler operation, I'd rather use the transpose. Okay? What is a D in that description? It's supposed to be a diagonal matrix. Well, the usual suspect there is the diagonal matrix whose diagonal entries are the eigenvalues. Whose diagonal entries are the eigenvalues of A. Okay? More explicitly, this is this. Okay? It's best to think of this as a block matrix, like so. No. Okay, that's your diagonal matrix. This is the identity matrix of dimension equal to the AM of lambda 1, and so on. Okay? So if you want to sort of fast forward this, in block notation, you can write it like this. So everything else is 0. This is block diagonal, like so. And AI is the same thing as AM of lambda I. Okay? Now, if you just look at these equations, okay, you're literally writing down the columns of A times Q. Okay? Then you just realize that this is nothing but AQ, so computed column by column. It just turns out that you have that decomposition. I'll write it here. AQ equals QD. That's what you get. Okay? And finally, you take this to the other side as an inverse, right? Cancel this out, send it here. But then, by virtue of the fact that Q is orthogonal, instead of inverse, you can write Q, D, Q transpose. Okay, that's item 4. Any questions or comments about this? Now, in a sense, we've actually seen this before, this format. In the previous, the previous time we saw that, it just wasn't that important to write the D in between. Where else did we see something of the form QQ transpose? We have seen this formula, maybe for some other letter. KK transpose, whatever. Think about it. Where did we see matrix multiplied by its transpose? I'll give you a couple minutes. You're going to know this for the midterm, okay? It does make a symmetric matrix, but so where did we use this idea of multiplying a matrix by its transpose to sort of come up with an n by n, let's say? This was like a geometric idea that, yeah.
We were using it for the Graham-Schmidt?
Ultimately, yes. So orthogonal projections, ultimately we did Graham-Schmidt whatever, and we wrote them as UU transpose as well, right? So we wrote them in that form. So it's pretty much the same idea, actually. This is just slightly more general. Okay? Because after all, orthogonal projections are supposed to be symmetric. Therefore, the spectral theorem ought to apply to them. Okay? So for an orthogonal projection, you can either go through this Graham-Schmidt whatever to come up with this UU transpose representation, or you can think of it as, oh, I was just applying to the spectral theorem. That UU transpose that we obtained for orthogonal projections is sort of like a special case of this. And here's why. I'll write it like this. Let W be a subspace what did we do there? Of dimension k, let's say. Okay. Then I have, by way of Graham-Schmidt whatever, an ONB for W. Yeah. Okay. And then we took these K, O, and B's, put them in one matrix as columns. And then we realized that orthogonal projection can be represented as UU transpose. Okay? This is a special case of this. What's the difference? Well, the difference, first of all, is in this case, U is not necessarily a square matrix. But an orthogonal matrix there has to be square. Well, what you can do is, well, you can look at orthogonal projection onto the orthogonal complement of W and get an orthonormal basis for that also. And if you were to put them together, that would give you a complete orthogonal matrix. Okay? So this is sort of like a cheap spectral theorem. You're sort of not writing down the matrices that you know are going to be 0 for your purposes. So let's say you have more vectors, O and B for W perp. Okay? Now, take these and take these as well. Okay? U, N. Since it is the case that identity is the same thing as projection onto W, and the sum of projection onto W and the projection onto W perpendicular, well, this is nothing but Q transpose. Rather mysterious. What is happening here is this, okay? If you were just looking at projecting onto W, you would just consider an O and B for W itself, okay? That would give you your U, and then if you were to multiply U transpose, that would produce for you orthogonal projection onto W. But in principle, you can keep going and add to this K tuple of O and B's more orthonormal vectors and still look at the same expression. Okay? If you can complete the whole thing to one O and B for Rn, you literally get an orthogonal matrix, and the same shape gives you projection onto the original space. In other words, you're not doing anything. And that's why for an orthogonal matrix, QQ transpose is the same thing as identity. I realize this is rather mystical. It might feel like I'm just like writing letters now at this point. It requires some time to sort of think about these things and do some calculations, I would say. Okay, good. I think there's a couple more words I want to say regarding this and spectral decomposition, but that's a good place to stop for today. Thank you. All right, let's start. Good morning. I'm going to take attendance today. There's still a couple of things I wanted to discuss regarding the spectral theorem. I want to say a couple more words about this. Let's write it like this. This implies A equals QDQ transpose. I want to say a couple more words about this. This is essentially the spectral theorem packaged in a matrix factorization form. So spectral theorem. What else? Well, yeah, I want to discuss how this is a generalization of this idea of representing an orthogonal projection this way, the product of two matrices, or rather, the product of a matrix with its transpose. It's a special case of the spectral theorem, really. And then once we understand this, we're going to be able to look into first the spectral decomposition, and then singular values, NSVD. So the point of singular values in SVD, singular value decomposition, is going to be pretty much the spectral theorem, but now you want to apply the spectral theorem to any rectangular matrix whatsoever. 5 by 7, all these things, okay? You don't even require that A is a square matrix, and you try to sort of force applying the spectral theorem to this matrix, and the best you can do is the singular value decomposition ultimately. We're going to see. So let's remind ourselves. Spectral theorem was all about consequences of starting with a symmetric matrix. Okay, it had a bunch of consequences. For instance, eigenvalues are real. Any two eigenspace is perpendicular. Gm for any eigenvalue is equal to its Am. There's an orthonormal eigenbasis for Rn, the space on which A is acting. And the final item was this, decomposition. And what was the content of these matrices? Well, we had an orthonormal eigenbasis for Rn, u1, u2, whatever, all the way up to un, right? Orthonormal eigenbasis. So what does that mean? Let's remind ourselves. First of all, any two vectors in my basis is orthogonal. So if I dot any two vectors, that gives me 0. If, well, we can write it like this. I is not equal to j, 1. If I is equal to j. That's the orthonormal part. Orthonormal. And then if I apply A to any one of these, it's going to be a some scalar multiple of the input vector. Lambda, I don't know, lambda 0 times ui. Okay, that was ONEB. And Q in this expression, okay, Q, is the matrix whose columns are these. I can just take these n by n vectors, put them in one matrix, call that Q. Like this. And just to remind myself, sometimes I put sort of like these lines to represent that, oh, these are columns now. Okay? But since the columns are, since I have a square matrix whose columns are orthonormal, that's the definition, that's one of the definitions of Q being an orthogonal matrix. That is to say, Q transpose is identity, and Q transpose Q is also identity. Okay? And what was D? D is going to be the diagonal matrix with eigenvalues on the diagonal. Okay? And then what did we say? Well, if I apply, so let's look at this slowly. Again, this is what I'm trying to understand. Since Q multiplied by Q transpose is identity and vice versa, remember this implies, is in fact equivalent to saying that Q transpose is the multiplicative inverse of Q. Okay. And so I can start with this expression. Okay, this is the same thing as QDQ inverse. But then matrix algebra allows me to say, if I multiply both of these by Q, I have this. Okay. And note that what is this? It's like so. Well, A times Q is going to be that n by n matrix whose columns are the outputs of A, or outputs of these vectors under A. That is to say, these are like so. Matrix algebra. But then this is some constant multiple of u1. This is some constant multiple of u2, whatever, because all of these are eigenvectors also of A. Right? That's the vectors that we started with. Yeah. Eigen. Okay, so maybe I'll write it like this. So I don't want to use lambda 1, lambda 2, whatever. Well, we can say with multiplicity. Like this. I'll use a different letter here, just to not confuse this. So I'm allowing values to be repeating using different indices. Say mu. Greek analog for the letter m. Mu1, mu2, and then mu n, un, like so. But then I can think of this as, well, the u1, u2, un matrix with some column operations. So for instance, I can say, oh, I just took Q matrix, this guy over here, and scale the first column by mu1, scale the second column by mu2, and whatever, which would allow me to factor out these scalars as a diagonal. Like this, and then mu1, mu2 on the diagonal. Okay. So what I did was I started with AQ, I expanded everything, and I realized AQ equals QD. In other words, just by virtue of the fact that I have an orthonormal eigenbasis, I can go ahead and realize that AQ equals QD, which is the same thing as realizing this, which by virtue of the fact that Q is orthogonal is the same thing as this. That factorization that we were looking into. There are multiple ways of thinking about the same thing. Just wanted to go ahead and do it again. If you get confused, in my experience, what ends up being useful is, while you remember one or two items in the spectral theorem, and you sort of reconstruct the rest. So try to sort of deduce different parts based on certain examples or certain other items that you can remember. Okay? Now, I want to make sense of the idea that this representation that we came up with for an orthogonal projection is a special case of the spectral theorem. Okay? Maybe even before that, maybe it's going to be more useful to look into this spectral decomposition. sometimes you might see this factorization as the spectral decomposition. Sometimes they mean a different thing. The way I would like to imagine it in this context is, well, spectral decomposition is going to be a rank 1 decomposition of my symmetric matrix that I started with. Okay? What does that mean? I want to start with a symmetric matrix A, and I want to write it as a linear combination of rank 1 matrices. Rank 1 matrices are pretty much the same thing as outer products. Okay? I'll write it here. So, what I want is this. Given an n by n symmetric A, I want to come up with finitely many rank 1 matrices. So finitely many square matrices, each of whose R numbers are 1. So these are simple transformations, such that some linear combination of them gives me back A. I want to write A as a linear combo of rank 1 matrices, of rank 1 n by n matrices. That's what I want for spectral decomposition. And really, it all boils down to figuring out or rewriting this factorization. Okay, that's my Q. And then my diagonal is going to be like this. But just so that I can keep track of multiplicities, I'll write it like this. So I allow different indexed mu's to be the same for this notation to make sense in general. And I have that. Now, well, I'm going to do something, and I hope it's going to look familiar. Okay, and I'm going to ask you once we're done with this calculation. So let me take some matrix, some vector x, or n-dimensional vector. Okay, I'm going to look at ax. Ax. This is QDQ transpose x. Just substitute it, the spectral theorem. Okay. Let me just expand this part. Now, instead of writing the transpose of this, I'm going to write u1, u2, whatever as rows. And I'm going to put like horizontals. Okay. Now, I'm just going to do this matrix vector product. It's going to give me an n by 1 ultimately, and its coordinates are u1 against x, u2 against x, whatever. I leave these as is. Now I have Is this okay? Any objections to this algebraic manipulation? Right. U1 is going to have n scalars in it. X is going to have n scalars in it. And if I'm doing this matrix vector product, for the first entry of the product, Well, I'm just going to match the corresponding entries of the first row of Q transpose and the first column, which is the only column, right? Multiply the corresponding scalars, add them up. That's literally the same thing as taking this inner product. Okay? Now I keep going. The middle term is the diagonal. And in fact, while I'm doing that, let me, is this what I want to do? No, I want to leave it like this. Okay, that's fine. So I just expanded the D matrix, which is a diagonal matrix. Left multiplying by a diagonal matrix corresponds to scalar multiplying a bunch of rows, right? And so if I were to do this product, this gives me mu1 times u1 against x, whatever. Okay. Now I'm going to open up the Q. I'll write that again explicitly. First column, second column, dot, 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 nth column. And then I have these scalars. Okay. But then I can think of that matrix vector product as a certain linear combination of the columns of Q. Right? I can take these scalars, and I can think of this as a scalar of u1, the second scalar here as a scalar of u2, whatever, and I would add all of them up, and that would be the outcome. I'll write it here. I'll write it explicitly without this loop. So this is like this. Again, let's do a fast type check. That's a vector. That's a vector. That's a vector. But I'm taking inner product. So this is a scalar. This is also a scalar. So this whole thing is a scalar. I'm using this scalar to scalar multiply this first vector. And I do the same thing with every other column vector of Q, which initially, if you remember, came from my ONEB, orthonormal eigenbasis. Okay? Now what I'm going to do is this. I had used a similar trick before. Instead of thinking, just look at this part. Instead of thinking, oh, this is a scalar multiplication of a vector, since a vector is an n by 1, as a transformation, it goes from r to the 1 to r to the n. So I can change the orders of these. And likewise here. Okay, but if that is the case, what I can do is I can realize that this inner product, for instance, is nothing but u1 transpose multiplied by x and so on. So I can write everything like this. But then I can factor out this x, because x is a factor in all of them, to collect the terms. And that gives me the spectral decomposition. times x. Which if you want, at this point, you can use this for loop. This whole thing applied to x. Okay, again, let's type check. ui is an n by 1. It's a vector, normalized vector. So ui transpose is a 1 by n. N by 1 times 1 by n is an n by n. And this has rank 1. This is a scalar. So I'm taking a linear combination of ui transposes. And ultimately, since this has to work for any input vector x whatsoever, I have that capital A equals that sum. This is the spectral decomposition I need. And so now, you can just fast forward all this stuff. You can realize if you have an orthonormal eigenbasis, u1, u2, un, adapted to A, well, just look at these outer products of your basis vectors against themselves, scale them using the appropriate eigenvalue, and add all of these up. That's going to give you A. You have completely decomposed your original symmetric matrix into a linear combination of rank 1 matrices. I'll write it here. So if A ui equals mu I ui, ui against uj is 1. If I equals j, 0 otherwise. Right, that's ONEB hypotheses. Then A equals that sum. I'll write it here. You can just get rid of these Q's and D's, whatever. This is the spectral decomposition. Okay. Any comments or questions about this?
Why did mu I is the eigenvalue I?
Yeah. I mean, so with multiplicity though.
Okay.
Yeah. I'm going to give an example in a second. Yeah, so this is always like an issue. It's like in this business. Because you have eigenvalues and there are other things similar to this. It's like Lyapunov exponents, whatever. Are you going to use different indices for the same eigenvalue because it is repeating? Or do you want to just look at distinct eigenvalues? That's always sort of like a notational matter in this business. So both of them end up being useful. For some cases, you don't want to use distinct indices for the same scalar that is an eigenvalue. So you want to just index into distinct eigenvalues, index into the spectrum. For some other ones, it's more convenient to use distinct indices for possibly repeating eigenvalues.
And in this case, we're doing
Repeated, possibly repeating. So I'll write it. Yeah, this is an unfortunate situation. It's very confusing too. Because often what ends up happening too is that people don't tell you in which notation they're sort of writing things down, and then you have to sort of deduce from the context. Yeah. Any other comments or questions about this? But wait, there is more, okay? since each of these ui's are normalized and they're orthogonal, I can, at the very least, think of this piece as an orthogonal projection. Namely, this is nothing but orthogonal projection onto the span of ui. I can write it like that too. Okay. Now, what does this tell you? If you want to understand what your transformation, what your symmetric transformation is doing to Rn, instead of trying to understand the whole thing, you first go for the eigenequation. Solve the eigenequation, whatever. Ultimately, you get an orthonormal eigenbasis, distinct directions that are preserved under your transformation. And this says, instead of applying a to some x, what you should do is you should first orthogonally project your input vector to one of these eigenspaces and just use this scalar scalar number, because that's the definition of an eigenspace after all. On this eigenspace, A, this complicated matrix, acts as a scalar multiplication, turns into college algebra, okay? It's just that it turns into different types of college algebra in different directions. Okay? So you can take your matrix, your input vector x, right? So instead of looking at ax, first take this x vector, your input vector, orthogonally projected onto the span of ui, do college algebra there, just scalar multiply by mu I. But now you chose in which direction you orthogonally projected. Now you have to compile everything back together to get back what ax is. Okay? That's the meaning of this formula. I should mention this too. In physics literature, inner products, I'll write it here. So u, v, this inner product is written like this, okay? But they think of this piece and this piece as separate, okay? They think of it as this multiplied by this. And so to switch to the outer product, what they do is they flip the orders. So they write it like this. So v transpose, this outer product is like this. In physics literature, this is what they write. And this is what is called the bra-ket notation. And so in physics literature, this turns into this. Those of you who are going to study quantum information, whatever, are going to see this type of formula quite often. Quantum computing. But that's all they're doing, ultimately. The only complexity or complication here is that in the world of physics, you need to use complex numbers. So there's like some complex number thing involved there. But apart from that, that's all they're doing. Okay? Any comments or questions about this? Without understanding this formula, singular value decomposition is not going to make much sense. Okay? Question?
I'm just a little confused on so in the part where you have the vertical, like u1, u2, un, and you're multiplying the like scale dot products.
Where are you looking at? Here?
Yes, right there.
Okay.
It's like that. Actually, no, those are, okay, fine. I think I got it.
Okay. Right, so if I had, for instance, E1 here, 1, 0, 0, 0, that would index into the first column. Right? Just take a matrix and look at where it takes to 1, 0, 0, 0. That's just going to be the first column. So this coefficient is going to is going to be multiplied by the first column and so on. Yeah. We're not using anything new in a sense, but somehow it's like things we discussed in week 5 gets matched with things we discussed in week 2 and whatever. So it becomes like hard to sort of transition between multiple ways of thinking about the same thing. Any other comments? Okay. Now, what I want to do is I want to relate this to an orthogonal projection. Okay. I told you writing orthogonal projections as capital U transpose is a special case of this, or QDQ transpose, whatever. Now remember, some n by n matrix P is an orthogonal projection if and only if its square is equal to itself and it's also symmetric. So maybe example, let P be an n by n orthogonal projection. By definition, okay? That's by definition telling you that P squared equals P and it's also equal to P transpose. I need to assume symmetry also. If I don't assume symmetry, that's an oblique projection. Many of the things that we're going to discuss again works, but I don't want to sort of introduce more relativity in terms of angles and stuff. So we'll just stick to this case. Now, as any orthogonal projection is symmetric, spectral theorem should apply to it. Okay? Because spectral theorem only requires that you have a symmetric matrix. In this case, you have more, of course. You have that P squared equals P, and that's going to give us more. But at the very least, spectral theorem should apply to an orthogonal projection. Let me try to make sense of this. Let me try to use this P squared equals P equation. I want to say something like this. I want to come up with some spectral information about P, just based on the fact that P squared equals P. Well, if I had some solution to the eigenequation for P, okay, X is a non-zero vector. Well, P is the same thing as P squared. Okay. Exactly. But P squared is P times X. This would give me P lambda X. Take the lambda out. Lambda is a scalar. Apply eigenequation again. I have this. So whatever this lambda is, I'm assuming that there's a solution, and you can always assume that there are solutions. It is required that lambda x equals lambda squared x. Consolidating, I have this. So I'm saying x is some non-zero vector such that if I were to use this specific scalar, that scalar multiple is 0. The only way that can happen is if the scalar itself is 0. which means any eigenvalue of P has to be either 0 or 1. It cannot be any other eigenvalue. Is either 0 or 1. Okay? That I obtained only using p squared equals p. So if I were to look at the spectrum, I have only so many options. So for instance, if n were equal to 3, let's do it. So in this case, for instance, I can have this, I can have this, I can have this, or I have the identity. Okay, in terms of the spectra, here I have only one blip at the origin, two blips like this, two blips like this, and one blip here. These are all orthogonal projections, and these are ultimately the only diagonals you should be able to obtain using the spectral theorem, right? Because when you apply the spectral theorem to P, ultimately P is going to be Q diagonal, Q transpose for some Q orthogonal. So these are going to be the only possible Q forms you're going to be able to get. Okay? In a sense, up to a passive transformation, these are the only possible orthogonal projections in dimension 3. Now let's try to make sense of this. Saying that my orthogonal projection is the 0 matrix tells me that I am orthogonally projecting onto the 0 dimensional subspace. In this case, you see, I am orthogonally projecting to the x-axis. Okay, so I'm projecting onto a one-dimensional subspace. Here, I'm projecting onto a two-dimensional subspace. Here, I'm projecting onto a three-dimensional subspace, but since my space is three-dimensional to begin with, that has to mean that my transformation is identity to begin with. Okay? So these are all possible cases up to passive transformations in the case of n equals 3. Maybe I should write Q here instead of P. Or D, should write D. D for diagonal. Okay? And you see, some of the eigenvalues could be 0. That's fine. Symmetric doesn't say much about 0 or non-zero eigenvalues. Okay? Let's continue. So that's like to the side. That's the case when n equals 3. Now, again, by virtue of the spectral theorem, which I can apply to this orthogonal projection, I should be able to write P as a sum like this. But in this case, these scalars, which ultimately were eigenvalues, well, they can be only 0 or 1. Okay? For u1, u2 dot dot dot, uk, I'll write it ur, and on, I'll write it like this actually. ONEB, okay, we have that P equals this. So you choose 0 or 1 according to the eigenvalue, and then UI transpose. But certainly we can arrange it so that the first however many entries in the diagonal is 1. And indeed, when you think about it, since the column space of P is the subspace onto which P is orthogonally projecting to, I can write it. Like this. UI transpose is an ONB for column space of P, and consequently R is equal to the rank of P. Because note that in this case, for an orthogonal projection, the column space is the same thing as the eigenspace associated to 1, and the null space is the eigenspace associated to 0. I'm not going to calculate this, but this is a very nice equation to sort of ponder on. So column space of P and the null space of P. Column space of P is the eigenspace associated to the eigenvalue 1, and null space of P is the eigenspace associated to 0. That's pretty nice. Okay. This is at the heart of really understanding the spectral theorem and the singular value decomposition as well. Any comments or questions about this? I know that this is somewhat mysterious at this point. I highly recommend that you sort of do some calculations and some sort of experiments and whatever to get these structural statements under control. Questions, comments? Okay. We have, go ahead.
When we were building our diagonal matrices,
Yes.
why wasn't the matrix where the diagonal goes like 1, 0, 1 a valid diagonal matrix?
What do you mean 1, 0, 1? Oh, it is a valid diagonal matrix, but I can just apply a permutation to just like.
So we just switched the eigenvectors?
Yes.
They're in order.
Exactly.
Okay.
I like sort of collecting the same eigenvalues in the same space.
Okay,
Like,
that makes sense.
if I'm writing my orthonormal eigenbasis, I would like the first however many associated to the same eigenvalue, and then the next however many associated to the second eigenvalue, and so on, so that the diagonal forms show up like this, which is freely available because even if you had permuted these diagonal entries, well, permutations are orthogonal, and orthogonal matrices form a group, so you can just let those permutations be absorbed by your Q matrix.
That makes sense.
This is like, you may not sort of see it at this point, but this is like a beautiful sort of theory. It just works. because of like 5 billion reasons. So if you can understand one interpretation, you can sort of extrapolate to the other interpretations and you'll be golden, okay? Any other comments or questions? Okay. Now I want to start talking about the singular value decomposition and singular values. Okay. Let's start slow. I think I'm going to set aside these quadratic forms and stuff that we had listed in the syllabus, but I'd rather we learn the spectral theorem and the the singular value decomposition. Singular values. Now, singular values are pretty much like eigenvalues, but they work more generally. Okay? What I want is, I want to start with an arbitrary n by n, and somehow I want to start talking about eigenvalues of A. This doesn't make sense because this is not even square, but we're going to force it by just applying the spectral theorem to this guy. Because I know that this, for sure, is both symmetric and a square matrix. We're going to apply spectral theorem to A transpose, and in a sense, we're going to take the square root of this guy. Okay, that's going to lead to the singular values and the singular value decomposition, which we're going to discuss tomorrow. Tomorrow, I'm going to also do some sort of a review where we're going to sort of go through some of these adjectives that are somewhat related, that sound very similar. Okay, thank you. I'll see you tomorrow. All right, let's start. Good morning. So I was planning to start discussing singular value decomposition and singular values today, but I thought since these topics are so, on the one hand, beautiful, mathematically deep, and important for applications purposes, I think what I'm going to do is I'm going to set these aside. We have all the ingredients pretty much. We're just going to compile them, but we're going to do that next week. Certainly, these are not included in the midterm on Friday in 2 days. So next week, according to our schedule, I wanted to discuss dynamical systems, at least linear dynamics. There's a bunch of different applications that are fairly cool, and they're also sort of closer to the way I understand linear algebra, in fact. So predator systems, Lyapunov exponents, something called an ergodic theorem, which is basically something like a law of large numbers. So we can sort of discuss certain versions of these. Or Google's ranking algorithm called PageRank. There's a similar thing, EdgeRank, that Facebook uses, or used to use back in the day. These are all sort of part of this Markov process paradigm. So I think what I'm going to do next week is we're going to initially study these, really understand what is happening, both looking into numerical examples and also some theory, some sort of calculations in matrix algebra. And then with the remaining time, I'm going to look into some dynamical systems and so on. Okay. Today, instead, I'd rather do a review. Okay. I want to do a review of many of these phrases or adjectives that apply to things. And I want to sort of relate different adjectives to each other, which one implies what, whatever, and sort of contextualize also the spectral theorem. Okay, so today's going to be a review. So here are a bunch of properties that a general n by n can have. So recall for a n by n, we start with these important properties, okay? A is orthogonal if A transpose equals identity matrix and A transpose A equals identity matrix also. Okay, that's what it means for A to be an orthogonal matrix. A is called symmetric if it is equal to its transpose. What else do I need? Oh, A is an oblique projection if its square is equal to itself. So these are all matrix equations, you see. A is an orthogonal projection if it is both symmetric and an oblique projection. If like this. And in fact, I'll add a new definition. I'm going to call A normal if it commutes with a transpose. Okay? This is new. So using this bracket notation, if you want, we can write it like this as well. A transpose bracket is 0. That's another way of writing the same thing. So this is a new phrase. All the other ones we had discussed. Okay. Now there are other phrases, diagonalizables, diagonal, all these things, but we're going to try to sort of put them all together in one flow chart over there. Okay. So let's start with this. Okay. Now here I'm going to try to draw a flow chart for different adjectives that could apply to arbitrary n by n's. Best type of a matrix I'm going to put up top, of course, this is diagonal. These are the best kinds. Okay. What is a diagonal matrix? It's a matrix that has non-zero entries only on the diagonal. Certainly, if I have a diagonal matrix, it has to be symmetric. Okay, because it doesn't have any other entries in the off diagonal. So diagonal implies symmetric. Okay. Well, orthogonal projection too implies symmetric by definition. Okay. And of course, orthogonal projection, again by definition, implies oblique projection. Okay. Now, let's try to remember, what does it mean for a square matrix to be diagonalizable? There's a phrase that we use, diagonalizable matrix. You should know this for the midterm.
There's a diagonal matrix and an invertible matrix such that, well, let the diagonal be D, the invertible be P, then A is equal to P times D times P inverse. I believe is diagonalizable.
Whatever, you're right. Whatever this diagonalizable is, well, it should be implied by diagonal. If you have a diagonal matrix, it should be diagonalizable also. Okay? Let's write here try to write the definition. So up to some passive transformation, up to a change of coordinates, your transformation is diagonal, right? So maybe your transformation is not diagonal with respect to the standard basis vectors. Diagonal means that, okay? But if you were to change your basis vectors, if you were to change your basis, with respect to this new basis, your transformation ends up being diagonal. So, means A equals P D P inverse, D diagonal, P invertible. At this point, I'm not requiring that P be orthogonal. Okay? P could be an arbitrary invertible matrix. This is just the inverse. Okay? Now, I want to give an example of a matrix that is diagonalizable but not diagonal. Okay? So this doesn't work the other way around. So you really need like a new phrase, is what I'm trying to say. Yeah, for instance, consider this. I'll write it here. Look at this 2 by 2. Immediately, you should say, oh, this is upper triangular. The eigenvalues are the entries on the diagonal. One eigenvalue is 2. The other eigenvalue is 1. Okay? You should be able to say this as a reflex. Okay? Immediately, I have that the spectrum of A is 1 and 2, diagonal entries. So 1 is an eigenvalue, 2 is an eigenvalue. Remember, and note that this certainly is not diagonal because you have a -1 here. But I hope that this is going to be diagonalizable, is the point. What was the case? Gm of any eigenvalue is sandwiched between 1 and am. Oh, that's 2. Okay. And we also know that the sum of all AMs over all eigenvalues has to add up to the dimension of the space. So whatever this is and whatever this is, their sum should be 2. They are lower bounded by 1, which means that both of them have to be 1. But if both AMs are 1, GM has to be 1 also. Okay? If it is the case that for any eigenvalue, GM equals AM, for instance, in the case of symmetric matrices, then that matrix is going to be diagonalizable. Okay? In fact, let's go ahead and compute this. So I know that GM of 1 is 1. That is to say, so I need one non-zero vector that is going to be an eigenvector for 1, and one non-zero vector eigenvector of 2. And so lambda equals 1, right? If I want to find an eigenvector for this, I need to subtract A from the identity matrix. And what does this give me? This gives me -1, 1, 0, 0. An eigenvector for this guy is a vector in the nulspace of this. Well, this just says -x plus y equals 0. So y equals x. I can just take 1, 1. Okay. So the diagonal direction is an eigenvector associated to the eigenvalue 1. To get an eigenvector associated to the other eigenvalue, now I'm going to use this scalar to scalar multiply the identity matrix, subtract A from it, and then look at the null space of the associated of the corresponding matrix. So 2, 0, 0, 2 minus A okay, now this is 0, 1, 0, 1. I need something in the null space of this. If I were to plug in xy, that just gives me y 0. So y has to be 0. I can just choose x to be 1, for instance. v2 could be 1, 0. Okay, that's an eigenvector. If I were to look at the matrix with columns this and this, I want to leave this here, and I want to leave this here as well. Let me just erase this little piece. So define P to be 1, 0, 1, 1. Okay? This is not an orthogonal matrix. Okay? If I were to dot this against this, the inner product is not 0. So this is not an orthogonal matrix. But it is an invertible matrix. Okay? 1's on the diagonal, upper triangular, determinant is 1. Determinant non-zero means invertible. This is an invertible matrix. It has an inverse. And in fact, you can compute the inverse to be this. Okay? And if I were to look at the diagonal matrix with eigenvalues on the diagonal, okay, PDP inverse is going to be A. I'll do that here. Okay, you can multiply in any order you want. Let's do these two first. Leave the first row. Multiply the second row by 2. And then this gives me 1, 1, 0, 2. This is not the matrix that I started with, though. Okay. You're right. There's a mistake. What your colleague is suggesting is that the order here is wrong. Or the order here is wrong. Something is wrong. Okay? This is very important. This is always the case. You take your eigenvectors, put them in a matrix, okay? That's fine. But when you look at the diagonal, you need to list the eigenvalues in the correct order. Okay? Because in this case, I took as the first column the eigenvector associated to 2. So if I'm going to use this as the first column, well, the first entry in the diagonal better be this guy. Okay? So let's do this correction here. It's like this. Like this. Now I'm scaling the first row by 2 and then leaving the second row. So that's 2 minus 2, 0, 1. And then when you multiply this, that's going to be 2 minus 1, 0, 1. And now it works, you see. So the order of the eigenvectors that you put in the P matrix, in the passive transformation, has to match with the order of the eigenvalues in the diagonal matrix. Otherwise, it's not going to work. Make sense? Okay. So you see, and so are there any questions with this example? This is an example of a matrix that is not diagonal, but diagonalizable. Okay? Comments or questions? Now we have the spectral theorem to add to this flowchart. I'll say this too. In fact, spectral theorem goes both ways. In fact, spectral theorem says symmetric if and only if orthogonally diagonalizable. Okay. That's the spectral theorem. Spec theorem. Okay. Certainly, if a matrix is orthogonally diagonalizable, it sounds like you can diagonalize it in a specified manner. It should be diagonalizable. But the point is not vice versa. Because any orthogonal matrix is invertible. Okay? So for instance, this is an example of a matrix that is diagonalizable, not diagonal, also not orthogonally diagonalizable. That's by way of the spectral theorem. Spectral theorem says orthogonally diagonalizable is the same thing as symmetric. And certainly this matrix is not symmetric. Okay? Let's try to think of a matrix that is symmetric but not diagonal. Well, I can just put some non-zero numbers on the off diagonal. Let's do that. So for instance, I can just look at, let's not look at this, because this is more. Maybe I can add here, okay. Let's look at 0, 2, 2, 0. Okay, this is a symmetric matrix. Spectral theorem tells me that this is orthogonally diagonalizable, okay? But I don't get to say, oh, the eigenvalues are 2. It doesn't work like that. Well, in this case, I guess it does, but don't do that in general. So what are the eigenvalues? So symmetric, orthogonally diagonalizable. Let me think. Oh, that's okay. Okay, yeah. Sure. In the 2 by 2 case, things are rather nice, but that's because of the dimension. Okay. So I need to figure out the eigenvalues, okay? Look at the characteristic polynomial. In this case, things turned out to be nice, but don't just look at off diagonals in general. What is this? This is the determinant, okay, of lambda times identity minus my matrix A. Okay. Now, remember, so the thing you're trying to take the determinant of is a linear combination of two matrices. But you cannot distribute determinant over linear combinations. Okay? You can distribute determinant only over products. Trace you can distribute over linear combinations. Determinant, no. That's why eigenvalues and eigenstuff in general is complicated. Okay? It's hard to compute these things. So what is this? This is the determinant of this matrix, which is lambda squared minus 2 gives you plus 4, but you need to put a minus, okay? Oh, there you go. One of the eigenvalues is 2, the other one is minus 2. I should also mention, don't forget that you're going to have a minus from this side. It's always AD minus BC. Just because you have a couple of negative entries in the off diagonals in the 2 by 2 case, don't forget the minus, okay? You're going to end up with something different. But again, you see, in this case, the spectrum is plus or minus 2. Two distinct eigenvalues. I'll say this too, this is like a shortcut, and this works in n dimensions as well. If it happens to be the case that you have some n by n, such that the algebraic multiplicity of each eigenvalue is 1, such as that case, then that matrix is automatically diagonalizable. Okay? Not necessarily perhaps orthogonally so, but at the very least it's going to be diagonalizable. Why? Because you're saying AM of each eigenvalue is 1. If that is the case, well, GMs are required to be 1 also. In that case, things are diagonalizable. Okay. So just by computing these eigenvalues, I can say that A equals, I'll write it here, put the eigenvalues in the diagonal. Okay, that's your D matrix. There's a Q matrix. Now it's going to be orthogonal. Okay, not only invertible but orthogonal. Some matrix such that you're guaranteed that A equals QDQ inverse or QDQ transpose. Why do I get to do that? Well, because in this equation, Q being orthogonal means, well, Q inverse is the same thing as Q transpose. So, see, even without computing what this Q is, you can factorize it, and you can sort of leave it aside. Maybe you can give it to someone else. You can say, oh, compute for me an ONEB, whatever. I know it exists, but I just cannot index into the entries of this 2 by 2, you can say, depending on the context. But let's go ahead and try to compute a specific Q for us as well. Well, for lambda equals 2, I just need to look at this. I'm going to delete it in a second. This minus 0, 2, 2, 0. Which is just 2 minus 2 minus 2, 2. Again, 1, 1 would work here. Okay. So let's call this lambda 1. This is V1. And then lambda 2 equals minus 2. Now I need to look at minus 2 times identity. And I'm going to subtract from that A. So this is minus 2, minus 2, minus 2, minus 2. And this time, I can take v2 to be 1 minus 1. These are the diagonal basis vectors. OK? Good? Now note, automatically, this guy is orthogonal to this. Right? 1 times 1 is 1. 1 times minus 1 is minus 1. They are perpendicular. That is guaranteed by the spectral theorem. If you start with a symmetric matrix, which we did in this case, well, the eigenvectors are going to be orthogonal, insofar as they are associated to distinct eigenvalues. So I can go ahead and put these into Q. Again, I need to worry about the orders. So first column should be this. Second column should be this. OK. Now let's try to compute this guy to verify. I'm going to delete this part. So this is 1, 1, 1 minus 1, 2, 0, 0 minus 2. And then I need to take the transpose of this guy, 1, 1. Well, it is symmetric also in this case, like this. That's a row operation. Minus 2 plus 2. That gives you the row sum. Oh, let's do this slowly. 0, and then 4, and then 4, and then 0. Huh, that's not quite A. There's an issue here.
Your orthogonal matrix is not orthogonal. Wait, the basis isn't normal.
OK, very good. That's the complicating thing here. It is true that for this Q, OK, it is invertible. That's fine. Columns are orthogonal, but that's not sufficient for Q to be an orthogonal matrix. You need to normalize the columns. These are not of unit length. OK? That's an issue. So this doesn't work. What you need to do is you need to adjust the columns. What you can do is, because column operations are right multiplication, you can just put here a diagonal matrix corresponding to the magnitudes. 1 squared plus 1 squared is 2. Take the square root. That's root 2. Oh, I should be taking the reciprocal, of course. And then here, like this 2. So now this product is an orthogonal matrix. OK? Let's try to compute this. So you see, in these calculations, there's a bunch of pitfalls that you have to be careful with. And even though I'm just giving you a very simple example, in higher dimensions, in sort of matrices with less zeros, whatever, the same things work ultimately. It's just that the algebra is slightly more complicated. I'm just trying to stick to this more simplistic case so that it's clear that certain calculations work the way they do. OK? If you want, we can sort of consolidate this too. Well, in this case, things are nice, of course, because coincidentally, we came up with eigenbasis vectors with the same magnitude. Okay? In general, this is not going to happen. In this case, I can just take this 1 over root 2 as a scalar. But in general, this is not going to happen. In general, you're going to do some calculations, and then the magnitudes of the solutions that you come up with are going to be distinct, in which case the algebra is going to be more complicated. Never mind. So this is 1 over root 2, 1 over root 2, 1 over root 2, minus 1 over root 2. That's your orthogonal matrix. So let's write it. Like this. And again, in this case, yeah, okay. Yeah, so somehow in this case, we came up with a Q that is also symmetric, okay? Q is supposed to be orthogonal, not an orthogonal projection. But it might happen that the orthogonal matrix that you have is symmetric. That can happen too. So let's look at this guy. Again, multiply these two. The best way to understand these is to go through certain calculations and convince yourself, okay? If you do the physical labor, you're not going to be able to disregard the physical evidence, the experiential evidence that it works. So it's not going to help you to look at just the statement of the magical theorem. So that's a -2, that's a +2. Then I need to do this multiplication. Okay. 2 minus 2 is 0. That's 2. Plus 2 is 4. But in the denominator, I have the square of √2. So that's 2. 2, 4, again, divided by 2 is 2. And then this is going to be 0 again. So this is A. Now it works. Okay? Yeah.
So up there, when you did the Q times that matrix,
Yes.
can you go a little more slowly as to what, like, matrix or what? I know you used the number 1, but where did you get that from in order to compute the 1 over √2?
Yes. Okay. So let's write it here. I'm going to erase it, but I had this matrix, okay? So V1, so lambda 1, lambda 2. Lambda 1 was 2, lambda 2 was -2. I looked at the null space of the associated matrix and came up with an eigenbasis vector like this. V2 was 1, 1. The other way around. Okay? Now, to get Q, that is an orthogonal matrix, you need to have its columns orthonormal. These two are perpendicular, and if you were to start with vectors that are orthogonal, you can scale them however you want. That's not going to change the angle between. But I need, for orthonormality of the columns, I need that these vectors are of unit length. So I need to compute the magnitude of this, and I need to compute the magnitude of this. V1 against V1 is 2. V1 against V1 is norm squared. So the norm of this is √2. Likewise here. Okay. So I should be, instead of looking at the matrix whose columns are V1 and V2, well, I should be looking at the matrix whose columns are V1 divided by √2 and V2 divided by √2. Okay. So let's perhaps write U1 to be V1 divided by its norm. U2 divided by, U2 is V2 divided by its norm. So Q should be U1, U2. Now this is orthogonal. Okay. Maybe there is some confusion as to why this product works here. Does that part of the question as well? Well, I think, yeah, I guess you were fine here. Why does this work? You see?
That's what I was wondering. I'm like,
Oh.
I get why the top one works, but I didn't get why it was both possible.
Sure, but let's first realize that it works. So if I do this multiplication, I get this. Okay. The point is this. Left multiply. So if I were to take this matrix and left multiply it with this, that would correspond to scaling the rows. In this case, it works as well, but in general, it's not going to work. What I need to do is to scale the columns. Just like left multiplication corresponds to row operations, right multiplication with elementary matrices correspond to column operations. So if I want to scale the first column by something, all I need to do is to right multiply by the appropriate diagonal matrix. That's the idea. Yeah. Just to give an example, for instance, yeah, so 1, 2, 3, 4, 2, 0, 0, 1. Okay. Let's first do it the other way around. That's my A, 1, 2, 3, 4. At this point, we know that left multiplying A by this matrix corresponds to multiplying the first row by 2. Okay? Right? So this is the matrix, this is the elementary matrix that corresponds to the row operation. Scale the first row by 2. Okay? But if I were to do it the other way around, multiply this by this. Okay? Right? So this is going to correspond this time to scaling the first column by 2. Why? Because if I were to take the transpose of this, this is equal to this. Well, that means I need to be scaling by 2 the first row of A transpose. But the first row of A transpose is the first column of A. So you can think of it that way too. Does this make sense? Yeah. Any comments or questions? I want to add more things to the flowchart. Yeah, while we're at it, I'll give you an example. No, I'll hold on to that. Now, if I have a symmetric matrix, A equals A transpose, that implies normal. Okay. For a symmetric matrix, A transpose equals A, so the left-hand side is A squared, and so is the right-hand side. Symmetric implies normal. But also, an orthogonal matrix is normal, because both this and this is identity. Let me see, what else do I want to do? If I, in fact, allow myself complex valued matrices, there's a spectral theorem for normal matrices that says normal matrices are orthogonally diagonalizable using complex numbers. So unitarily diagonalizable is the proper word, but orthogonally diagonalizable with complex numbers. Okay, and again, the spectral theorem for normal transformations gives you this. We're not going to even discuss it any further. I'm just mentioning it just to perhaps give you a sense as to why all of these things are sort of so, confusing in terminology. And if something is orthogonally diagonalizable, it is also orthogonally diagonalizable with possibly complex numbers. Okay. I'll add one final thing. There's a couple more things that I can add using sort of complex things. So there's something called the unitary. There's something called the Hermitian. Those of you who are going to take more advanced stuff with complex valued things are going to learn these as well. But one perhaps important property again is whether or not the matrix is invertible. Out of all of these properties, okay, the only thing that implies invertibility is orthogonal. All of the ones could be non-invertible. So in general, when I put this implication, maybe it might imply, but in general, there are sort of counterexamples for the other way around. So invertible. Okay. So you could start with a diagonal matrix, say all zeros. That is a diagonal matrix. Spectral theorem applies, whatever. But it doesn't need to be invertible, you see. Any comments or questions? Just go through this flowchart, try to come up with examples. I want to give two examples. I'm not sure if I'll be able to finish all of them. First of all, so we discussed, let's see. We discussed an example for this, not, so symmetric but not diagonal. We came up with an example that is diagonalizable, but not diagonal nor orthogonally diagonalizable. I want to come up with an example that is an oblique projection, but not an orthogonal projection. And then I want to come up with an example that is a normal transformation, but neither is symmetric nor orthogonal. Okay. I'll write these down. So for instance, I think for one, I came up with this example in class before. Again, I'm going to stick to 2 by 2. I need an oblique projection that is not an orthogonal projection. So I need a matrix A whose square is itself, but is not symmetric. Okay? So I think this was the example. I think this was the example. So if I were to compute A squared, what is this? 1 minus 1, 0, 0. Okay. So you see, this matrix A certainly is so that its square is equal to itself. However, clearly, this is not a symmetric matrix. Okay? So this is an oblique projection that is not an orthogonal projection. Okay? And then finally, an example of a normal transformation, normal matrix that is neither symmetric nor orthogonal. And probably I'm not going to have time to finish this, but this is a nice example. Yeah, look at this. 1, 2, minus 2, 1. This certainly is not symmetric. In fact, it is skew-symmetric. If you were to take the transpose, you pick up a minus, or anti-symmetric is what people would say. It's also not orthogonal. At the very least, you see, even though the columns are orthogonal, they are not normalized. The magnitudes of the columns are √5. So this fails to be orthogonal. It fails to be symmetric. I'll leave it to you, though, however, that A is normal. It commutes with its transpose. Is normal. So somehow this complex spectral theorem would allow you to diagonalize this too, but you would require complex eigenvalues and so on. Okay, I think I'm going to leave this to you. This is a nice example. Look at eigenvalues, eigenvectors, whatever, just to have some sense. Okay, so that's it for today. We're going to have the midterm on Friday. Thank you.